Hello all, welcome. So we wanted to actually start our presentation with basically giving you a time sequence of what we are analyzing. So on the left-hand side, we have the plane sphere, and on the right-hand side, we have the spiky sphere, and on the top, we have the velocity contour plots, and on the bottom, we have the vorticity contour plots. So the reason we're doing this is to briefly introduce basically what you're expecting in the presentation, and then we'll delve into the details more. So here we have flow around a sphere on the left-hand side, and we can see that the wake that you get on the sphere is smaller than the wake that you get in the spiky sphere, and the shear layer formed, as you can see in the vorticity plot, is more continuous in the plane sphere, and it is more discontinuous in the spiky sphere. So more details of these are covered later on in the presentation, but this was just an introduction to what we are trying to do. So this presentation is about characterization and comparison of the flow around a smooth and a spiky sphere using particle image velocimetry. We have Andres Barrio-Zhang, we have me, we have Pranshul Sardana, and we have Nishanth Surianayanan. So the objectives of this lab are to experimentally acquire raw data for PIV for a smooth and a spiky sphere over a range of Reynolds number, which we, in our case is 1325 to 4571. We'll compare different ways to convert the raw TIFF files to BMP. We'll find good PIV configurations for the current acquisition because this whole class is about PIV, and so we have to figure out what is the best way to analyze the images. And then when we process, we will be looking at the velocity vectors, velocity contours, vorticity contours, and the streamline plots to basically analyze the two different cases that we have. So, but before we proceed, we actually should know what the basics of a flow around a sphere is like to be able to delve into the problem more. So here we have basically a figure of basically as we increase the Reynolds number, you can see that the flow drastically changes. So when we are at a very, very low Reynolds number, we have basically a creeping flow, and we have two stagnation points at the front and in the upstream and the downstream. As we continue to increase the Reynolds number, the flow basically separates, and this point of flow separation starts to recede more upstream. As we continue to increase the Reynolds number, there are a pair of counter-rotating vortices formed in the wake that start to travel downstream as with the continuous increase in Reynolds number. Finally, at very high Reynolds number, the flow basically becomes discontinuous, and there are various eddies that are formed. So here, I just wanted to show a quick animation of basically what flow around a sphere here at a Reynolds number of 10,000 looks like, and you can see that there are these vortices being formed, and as you keep watching the video, they tend to travel downstream. So for our case, what we are looking at is a flow around a sphere in a 1500 to 4500 range of Reynolds number. So what we observe is that there is a periodic wake shedding, as we saw in this image earlier. But what is the most important is that there are two kinds of drags that are in play here. First, we have the skin friction drag due to the boundary layer formation, and that boundary layer basically separates at some point along the sphere. So that is the point of flow separation. And in the wake region, we start with, so here the velocity is plotted, and we start with the uniform velocity. However, in the wake region, we actually have negative velocity. And due to this decrease in velocity, we have a pressure drag, pressure drag that is caused in the wake region, and this actually acts like a suction, basically, which basically pulls the ball back if suppose the ball is moving in the leftwards. So what we wanted to understand is that if for example, so the two forces that are at play here are the skin friction drag and the pressure drag. So what we want to do here is we want to look at if we add certain kind of unevenness to the outer surface of the sphere, does that lead to any changes? So the two examples that we have from literature here are the golf ball and the micropillars that I'll come to later. So in a golf ball, what happens is that you add these small dimples in the smooth sphere, and that actually delays the point of flow separation. and the wake that you get is actually smaller. So what happens is that even though you increase the skin friction drag in the golf ball uh, due to the turbulence that you have, the pressure drag that you have is actually smaller in comparison to the smooth sphere. So even though the skin friction drag reduces, the pressure drag reduces by much larger value, and that is why the golf ball with the dimples is able to travel much further in comparison to the smooth sphere. Similarly, in this paper by Evans et al. In 2018, which is by Professor Luciano Castillo in the ME department here, they basically found that if you have these micropillars, so you can see that these are 100 micrometers apart, and these are by scale. What they have is that you have certain regions of high pressure and low pressure formed in this region, and they actually lead to again the same phenomenon of flow separation delay when they attach these micropillars to the top of the hydrofoil or an airfoil, which is seen in the experiments. So you can refer to this paper if you want more details. So here we wanted to basically compare. Here we have the golf ball, and we have the sphere, and these are the CFD simulations. And we can see that the flow separation point of the sphere is actually earlier than for the golf ball, and the wake that you get in the golf, the wake that you get in the sphere is actually larger than the wake of the golf ball. And finally, the most important point, one of the also the most important points, is that this point where the flow is separating for a sphere actually oscillates between this on the surface basically. However, for the golf ball, that point of flow separation is actually steady. Is at one particular location. So because of that, the golf ball is able to fly at a much steady way in comparison to in comparison to the sphere, and that's why you can get the golf players can get much more control when they hit the golf ball in comparison to a spherical ball. So what are we trying to compare here? So here we have a spiky sphere, which you can see an image on the right, and we'll get to the exact configuration later. But what we want to see is that what happens due to the presence of these flexible, so these spikes that are added to the sphere are actually flexible. So we want to know what happens due to these flexible structures added. Does this actually lead to wake reduction as we saw for the golf ball? And are the flow patterns different in comparison to that of the sphere? And this whole lab is about learning how to do PIV. So do we need any kind of different PIV settings that we need to change to analyze the flow around the sphere?
So getting our hands dirty now. We constructed two different models here. One was the plane sphere and other one was the sphere with spikes. So in order to construct these models, we had two criteria. The first one is that the structures we chose should be transparent. So it's because we did not want it to restrict ourselves from imaging the upstream. And if we use an opaque object, it just blocks the light for upstream simply because the laser light is placed downstream. So in order to construct the plane sphere, we bought this Christmas ornament ball from Amazon, and this is a hollow ball. So it helped us in a way that we can fill this ball with water, so we can have a refractive index matching with like the water of the water tunnel, and the buoyancy. There is no buoyant force on this object anymore. So the plane sphere had a diameter of 50 millimeters. And while going to the sphere with spikes, we reduce this base diameter to 40 millimeter for a reason I'll explain in a minute. So in order to construct these spikes, we iterated over multiple options, like we can fabricate individual of these spikes and place it on top of this spherical object. But we ended up with using a stress ball. So this is something we found on Amazon again, that there are these stress balls which already have the spikes. So it's a good enough representation of the spiky ball, as we did not had any biases towards the dimensions of the spike right now. So anything which was easy to obtain is what we chose. So other than the base diameter of 40 millimeter, the diameter of the thickness of this skin was 1.75 millimeters. So when we coat it around, when we glue it around our transparent ball, we have a base diameter of 43.5 millimeters, which is still a bit lower than the 50 millimeters that we saw. But each of these individual spikes, they have a height of 4.5 millimeters. So taking two of these spikes, so the new diameter, it becomes 52.5 millimeters, which is a bit higher than the plane sphere. So now the lower and higher ranges of our diameters here, they encompass our plane sphere. So these diameters, they had a pitch of around 50 millimeters, and these spikes, these were actually tapered. So we had a base diameter, and then this base diameter, it reduces as we go away from the sphere. So these balls were mounted on an acrylic stand. So in order to do that, a rod was used, a metallic rod was used, and we wanted to use a rod as thin as possible. So we found this rod on Amazon again. So the acrylic stand had a screw there so that we can move the sphere as we want. So we just moved the sphere in order to make sure that the light sheet is placed at the center of the sphere, or the spiky sphere. So in our experiment, 30 micrometer silver coated glass spheres were used as PIV tracer particles. So the light sheet creation was done by a ND-egg laser. And so the laser used was ND-egg, and then the sheet creation was done by a cylindrical lens of power minus 15 millimeters. Now switching to Andres for configurations. You might be on a mute, Andres.
Sorry about that. So going into our image acquisition configurations, we basically had a picture resolution of 1600 by 1192. There was a time difference between the image pairs of 3 milliseconds, which was also determined by both lasers going on and off. And between the image pairs, we had 100 milliseconds, which actually determined the frame rate or frames per second in the videos that you saw at the start of this presentation. To find the scale of how much a pixel represents in terms of meters, what we did is we used a sphere, or the sphere of known diameter, and in the images, we basically processed them to count the number of pixels in the diameter, and then we divided that diameter per pixel, which resulted in 66.67 microns per pixel. Another thing that we had to, or another parameter that we had to control was also the aperture. So the way we did this is we chose the aperture based on trial and error by testing multiple ones until it gave us the biggest possible value without a minimal image saturation, which for our case was f16. Finally, we also adjusted the focal plane by moving both the camera and the models. The model to be basically being hit by the light sheet correctly, and then adjusting the camera in order for the area of focus to be at that plane where the light sheet is hitting the object. So it's not changing. Okay, so here's a schematic of our experimental setup. We basically had the laser that was with an optical system creating a light sheet that illuminated the test section, and within the test section we had the 30 micron particles that reflected that laser and the object, in this case the smooth sphere and the spiky sphere. The laser also imaged it from a downstream opposite to the flow direction in order for us to see the flow structures that would form in the wake of the object. And finally, as well, we varied the pump frequency in increments of 5 hertz overall, and waited 60 seconds per increment in order to reach a steady state flow. And we checked using a single pair and inside to see if we were getting good velocity vectors throughout before we employed our own specific PIV processing. So We also created a test matrix in order to know what the Reynolds numbers for the both the plane sphere and the spiky sphere were. We used the formula that we're all acquainted with for the Reynolds number. And basically what we did is we, at every frequency, we averaged the vectors far away from the sphere in order to get the free stream velocity. And using this free stream velocity and the parameters shown here, we calculate this number. And as you can see here, also, the free stream velocities for both cases are quite similar. We also compared these values to a case of uniform flow without any object submerged, and it gave us comparable results. But we'll go more into in depth on to what this means in the results section for this presentation. But before we process the PIV images, we had to do some image pre-processing in order to extract the particles and accurately track them within the flow. So what we first noticed is that there's a bunch of pixel intensities, a wide gamut of values within the image. So specific to this histogram of intensities, this is for a case where there's no object in the image. So it's just mostly the particles and the background for the flow. And most of the pixels actually reside in a pixel intensity that's much lower than the actual particle intensity. So these pixel intensities had to be neglected so we could extract the particle or pixel intensities that corresponded to the particles within the image. So we could then track them per image pair. So our first approach, which is the most simple one, was basically just to do a simple conditional statement that spanned the entire image. So within a certain threshold, the first thing that was done was to calculate the maximum pixel intensity in the image, which corresponded to the particle intensities or the particles within the image. And then using a threshold in a conditional statement, you can extract the particles within the image. However, when doing this, we actually noticed that there was an uneven illumination between the laser A and laser B. As can be seen here, from the simple contrast adjusted image is not as clear, but once you extract the particles, most of the particles that are visible are only seen in the top part of the image, whereas in the bottom part, there are basically no particles at all. Yeah, this effect was reversed when using the laser B, where most of the illumination was at the bottom of the image. So to counteract this effect, the strategy that we chose to employ was to basically divide the image into smaller pixel windows and then find the maximum intensity in those windows and extract the particles therein. This way, we could compare the particle intensities with respect to the local intensities or the local background. And once we perform actually contrast adjustment locally within these windows, all the pixel intensities are pushed within the same thresholds. So when you rebuild the image using these small pixel windows, you can actually extract all the particles throughout the image at the same pixel intensities. However, this also presented a complication when using the objects. Even though the objects were transparent and we filled them with water for refractive index matching, we were still getting higher pixel intensities in and around the object that were considerably higher than that of the particles. This, when employing the small window algorithm, resulted in actually a dark halo or a darkened area around the object, since the boundary of the object was of much higher intensity than the particles. So a way we thought to counteract this effect was actually to first calculate the background image by averaging all the images from laser A and laser B correspondingly, and then subtracting that from every image before we extract the particles. And this helped in removing certain intensities, for example, from the acrylic stand and also from the non-even background illumination. But in the end, it didn't really remove the object from the image I'm thinking this is because of the particles moving throughout the flow. It actually decreases the overall intensity. So even though it subtracts those intensities, it still is at a higher degree than those of the particles. So we were still getting the dark halo effect. However, in the end, at the expense of computational time, what we did is we just reduced the window area to 20 pixels by 20 pixels to mitigate this, again, this dark halo effect. But we still performed the background subtraction, as it also allowed for a more even distribution of particles throughout the image. Now, Nishanth will go into our processing parameters that we used with the Prana PIV software.
Yeah.
Nishanth, can you ask for control?
Yeah.
You guys got this all figured out.
Also, your video is off, Nishanth.
No. Oh, is it? No. Like, I mean, can you guys
Now
see
I
me?
see you.
Okay.
Now you're there.
Okay. Yeah. So for our PIV analysis, we used the Prana software. So Prana is a software which is developed by Professor Pavlos Vlahos research group. So before we perform our PIV analysis, we do something which is called as masking. So through masking, we basically are telling the software the regions where we want to perform our PIV evaluation. And the regions where we don't want to perform PIV evaluation. And since, in our flow field, we have the sphere, and within a sphere, since there is no flow and no tracer particles, we don't want to perform any PIV processing within that place. So this is the mask that we input to our Prana software, and this basically has the same image size as our captured images, and we are just assigning a pixel intensity of 0 in regions where we don't want to perform any PIV evaluation, and we are just using a maximum pixel intensity where we are basically just whitening the image to show that this is the regions where we want to perform our PIV evaluations. So after applying this mask on the image on the left, you can see that the grid points for our PIV evaluation is placed only outside the sphere. Yeah, and for our PIV analysis, we use a multi-grid scheme. So in a multi-grid scheme, so when you use multiple passes, the grid spacing as well as the window sizes can be changed in passes. So for example, in our first pass, if we have a sparse grid spacing, we can go to a much finer grid spacing in our second pass, and basically our velocity estimates from our first pass is interpolated onto the grid locations in our second pass. So for our selection of window sizes, so we did it based on two rules. So one is the 1/4 rule, and the other one is based upon the minimum number of particles. So for determining our first pass window size, we use the 1/4 rule. So the 1/4 rule is just states that your window size has to be 4 times the maximum displacement, and this is basically done to prevent any aliasing effects. And our second consideration for selecting our last pass window size is the number of particles. So in order to have a good signal to noise ratio, it's always necessary to have at least a minimum of 5 to 6 particles within our each interrogation window. So based upon these two conditions, we selected our first pass and second pass window size to be 128 by 128 window and 64 by 64 window respectively, and we used a maximum of 6 iterations in each passes in order to obtain convergence of each pass. And we apply validation in both these passes. I'll get to validation in the next few slides. And I also apply a Gaussian smoothing in my first pass in order to have a smooth transition between the velocity vectors in the entire flow field. However, I do not apply any smoothing in my last pass, as this will basically smooth out the higher order features such as the vortices and eddies um, in the wake of the sphere. And we use a 3-point Gaussian estimator for finding the subpixel peak location. So we use for the processing method, we use a window deformation scheme, and for the correlation type, we use a standard cross correlation, which is basically just the FFT accelerated cross correlation method, and yeah, now going to validation. So validation is nothing but like an outlier detection and correction. So basically, we classify a vector as an outlier if there is like an abrupt change in the velocity vector magnitude compared to its neighboring vectors. So there is like two types of validation. So one is velocity thresholding, and another one is the universal outlier detection. So in velocity thresholding, if suppose basically we know that the maximum and minimum ranges of the velocity components in our flow field. So suppose our maximum value of the displacement is going to be just 5 pixels per frame, then we can basically like set um, a threshold where our if the maximum displacement through our processing is going to exceed this 5 pixels per frame, then that is going to be classified as an outlier, and it's going to be replaced by a neighborhood interpolation. And a universal outlier detection is where each velocity vector is compared locally to its nearest neighbors, and if it exceeds from if it deviates a lot from the mean of the velocity estimates in that region, then that's again going to be classified as an outlier, and a local interpolation is done to replace that particular vector. So yeah, I just wanted to show one like so the velocity vector field that we got like an and also wanted to point out like some regions where we got a few bad vectors, and yeah, these bad vectors are basically observed at the top corners of the image. So this is a zoomed in image of this the upstream of a sphere at the top corner, and sorry, yeah, and you can see that the number of particles in this region were very less, and this reduced the signal to noise ratio in these interrogation windows, which resulted in bad vectors in these regions. However, since our region of analysis primarily lies downstream of the sphere, this should not affect our post-processing. Yeah. So yeah, so I just wanted to point out the effect of validation here. So this is the processing results that we obtain if we do not do any validation. And as you can see over here, we see quite a few number of spurious vectors, which are clearly out of place over here. And if we use validation, we get much smoother velocity vector field. Yeah, so moving on to our results. Yeah, so first, yeah, we just sorry. Yeah, okay, yeah, yeah. There has been Yeah. Okay. So over here, we are just making a plot of the free stream velocity at different water tunnel frequencies, and for both the plane sphere as well as the spiky sphere, we calculate the free stream velocity by averaging out the velocity vectors far away from our sphere, and this is basically made as a plot over here, and we fitted a line of regression, and as you can see from both these equations, the slope of from both these straight line fittings is almost the same, and the R square for both our fittings is close to 1. So this is how we validate that our processing is parameters chosen was correct. Yeah, over here, yeah, we just wanted to show the effect of the flow separation, the point of the location of flow separation with Reynolds number, and we plotted the streamlines, and on the figure in the left, it's for a Reynolds number of 1523, and the figure on the right is for a Reynolds number of 4571. And as you can see, as the Reynolds number is increased, the point of flow separation moves upstream, and yeah, this is because the adverse pressure gradient increases as the Reynolds number increases. Yeah, and this is just a tabulated tabulation of the x by d locations at which the flow separates, and we find that the point of flow separation moves upstream as the Reynolds number increases. Yeah. So now Pranshul will be presenting the rest of the results.
So after obtaining our vector fields, we did a couple of post-processing steps on top of those vector fields. So the two interesting results that we wanted to extract were the velocity vectors and so the velocity magnitude vectors and vorticity vectors. So the thing you see right now is a comparison between higher Reynolds number for a plane sphere, and this is a velocity plot. So for both the velocity plots, the blue thing that you see here, it's actually the masked out region of the sphere. We cropped it down to the area of interest so that the visualization is a bit more better. The red dotted line, it represents the circumference of the sphere. So other than that, the red regions above and below, so these red to blue changes, it shows, so the blue ones show a low velocity and the red ones show a high velocity, and the velocities are normalized with their respective free stream velocity. So it can be seen that for a lower Reynolds number, the wake region, which is this blue region inside of this red region, the wake region, it shrinks quite rapidly as compared to a high Reynolds number. So this is something we expect of a low Reynolds number flow, that the wake region, it does not, the width of the wake region, it reduces pretty quickly. And these results can be can also be seen from our post-process results.
Hey, Pranshul, just to be clear, so I think what you're doing is plotting normalized absolute velocity, right? Because you've gone from 0 to 1. Is that correct? Not just horizontal velocity, which should show a flow reversal.
Yeah, these are the absolute values. It's just that the reverse values are also shown with the same color.
Well, I think if I'm reading this correctly, then you're plotting the magnitude of velocity.
Yeah, this is actually the magnitude of velocity.
Okay.
Normalized by the free stream velocity.
Yeah.
Okay, I got it. Go ahead.
We get to the actual velocity values at the end of the presentation.
Okay.
So when we move to a sphere with spikes, even though we have lower Reynolds number, so the Reynolds number here were calculated based on the diameter of the sphere with skin, not with the spikes. So the spikes are removed. We just wanted to get an estimate of what Reynolds number is there. But yeah, we can see that even if the Reynolds number is lower here, our wake is relatively wider. So it's kind of safe to say that because of introduction of these spikes, our wake, it behaves more like a turbulent wake. And if we go with higher Reynolds number, it's the width of the wake is still pretty much the same. It does not decay quite rapidly, which is there for high turbulent or high Reynolds number flows wakes. So while comparing our plane sphere and spiky sphere on similar Reynolds number, we can see that even if the Reynolds number was a bit lower for the spiky sphere, because of this introduction of these spikes, our wake is behaving more like a turbulent wake. So we can see some regions with high velocity magnitudes in the wake region for the spiky sphere. So it's very interesting to see that just by introduction of these objects, we can change how the wake should be even without changing the characteristic lengths of our system. So while comparing these two at higher Reynolds number, the difference is not that clear. Both the wakes are more wide for longer periods. But yeah, this is a bit redundant, but it's just to reinstate that at lower Reynolds number, the sphere with spike, it behaves very different than the plane sphere. So next, the effect of Reynolds number for vorticity was plotted. So what you see here is that the green spots here are again the sphere which is masked out. The red dotted line is the circumference of this sphere or this mask. And now we have a limit of -20 to +20 for vorticity. And anything which was outside this, so the results were cropped to this value. So anything which is outside this value was thresholded to ±20. So we can see that on the top of the sphere, we have this blue shear layer. It's more prominent with a bit higher Reynolds number that the shear layer is continuous. And at the bottom of the sphere, we see a positive value shear layer. So it can be seen at lower Reynolds number that the shear layer, this is actually contracting. The width of this, it's going towards the center more. So it reinstates that our wake region, the width of the wake region, it's reducing quite rapidly in case with no spikes and low Reynolds number. But when we go with the case with spikes, we can see that the graphs are a bit more chaotic. Firstly, our shear layers are not super continuous. We have higher discontinuities here, and the wake region, it has high vorticity. So we can see a lot of features with positive and negative vorticities in the wake region. So while comparing a plane and a spiky sphere, we can clearly see that because of this introduction of these spikes, our wake is not only the width of the wake, it remains consistent for a longer period. The wake is more energized. So this reinstates that just by adding of these spheres, our flow behaves more like a high Reynolds number flow. So we also compared these for high Reynolds number, and the results are a bit redundant. But yeah, the wake is more energized. That's the basic thing here. So now we have averaged out. So we averaged out our vector fields for 150 images, and Pranav can take over from here. You're on a mute, Pranav.
Sorry. So here we have plotted the average. We basically took average of 150 images and we plotted basically the wake. And we also took average of the velocities at this particular black line at different locations, and we plotted the velocity actually. So you can see it starts at at the free stream velocity. However, in the wake region, we get a negative negative velocity, and then it comes back to being positive again. And for the plane sphere, we see that the wake is smaller, as we have discussed previously already. For the spiky sphere, we see that this region where, the wake is larger, first of all, and this region where the velocity is negative is also larger, which means that the suction that is, the pressure drag that is there in the spiky sphere is actually larger than the plane sphere that we had. Finally, so to conclude on all the things that we have discussed so far, so we have seen that in the plane sphere, the location of the flow separation basically recedes upstream with an increase in Reynolds number, and the width of the wake and the pressure drag basically increases with the Reynolds number. Also, because of the spikes, the width of the wake doesn't reduce for even lower free stream velocities. So we were not able to see any pattern there, and the shear layer that we were getting is not so smooth. So going back to the initial hypothesis that we had, which was about would adding these spikes on top of the sphere on top of a planar sphere, would that actually reduce the drag? And the answer to that is no. But how did it reduce the drag for the micropillar structures that we saw and the golf ball that we saw? So our analysis is that for the golf ball, the spheres actually the dimples on the golf ball are actually much smaller in comparison to the unevenness that we have added on our sphere. And the micropillars that were added by Professor Castillo in his group were on micro scale, and the scale that we are looking at, our spike was basically 4.3 millimeters long. So that is why, because these spikes that we have are much larger in comparison to what the other examples that we saw, that's why it actually adds more turbulence to the fluid flow in comparison to when it is compared with the plane sphere. So thank you, and we would take questions now.
Yeah, not bad on the time. Nice job. So let's, I'll ask for any questions from the class first before I take all the good questions.
So I wasn't actually in class this year. Is there no way to do low Reynolds flow?
Yes, you can basically, just change it to a very viscous oil. You can buy some oil and do the experiment there. So that would be one way to do it.
Is there an easier way?
Use a smaller ball.
It's not very hard. So basically what you can do is you can buy a tank. Basically, you don't have to do it in the water tunnel. You can buy a tank and you can fill it with oil, right? And then you can fill it with the PIV particles that you have. Still create all the laser sheet and everything, except now you can basically move the ball relative to the flow. So instead of changing the velocity of the fluid, you are actually moving the ball. And if you do that, I think you'll be able to see the creeping flow.
Okay, cool.
What you're talking about.
Right. Actually, Patrick, your question is a good one because the motivation for this project was a low Reynolds number flow.
Yeah, exactly. That's what I was asking.
Yeah. So, what can you guys say about that? Like, if you optimized everything in this water tunnel, could you do a low Reynolds number flow?
I mean, going to creeping flow, it's super tricky because, our object is, we have to take an object which is comparable to the particles. And this can also create some additional problems. But yeah, so we are not modeling it as a corona particle anymore. That was a bit more, it was not well planned. So, but a spiky sphere, like just knowing the effect of adding additional objects on top of a plane sphere is the study. So we are not restricted for a low Reynolds number anymore.
Yeah, if we had done it in oil or something like that, then we might have been able to achieve. But for a coronavirus, for example, the Reynolds number would be like 0.001. So it is much, much less than 1. So we would really have to go into microfluidics area to be able to do some kind of tests in that. So that was the problem that we had. So that is why we changed the analogy of the problem that we were studying.
Yeah.
Well,
Yeah, there is no flow separation occurring in a coronavirus. So basically, so
well,
yeah.
one thing, so just to maybe refocus Pranav's statement, you could study the behavior of a coronavirus if you can get to a Reynolds number less than 1, let's say 0.1. If the real Reynolds number for the coronavirus is, let's say, 10 to the minus 4, as long as you can get to 10 to the minus 1, you get to the right flow domain, and then you can scale everything down to 10 to the minus 4 or whatever. So but I don't think there would be any way to slow down the water tunnel enough or to make your sphere small enough that you could actually do a creeping flow measurement in our water tunnel. Good question though, Patrick. Other questions?
Yeah, could you guys go to the your image pre-processing? I was a little confused on if you I thought you said you subtracted a white value from the whole image. Is that what you guys did? Back a couple. I think maybe.
I'll give up control. Andres can take
Yeah,
it.
I can give you the control. So Austin, right?
Yeah.
You can just can you ask for control?
Yeah, let me see if I can. Yeah, request control. All right, there you go.
I like the little icon with your faces on it. It's kind of funny.
Let's see if I can find it real quick. Oh, right here. Can you explain what you did here again?
So that is just to show that most of the pixel intensities or most of the pixels have a lower pixel intensity. And those account for most of the pixels within the image, which would be the background and the object. Like the higher intensity pixels, which are the particles, are more sparsely distributed through the image, and they're much smaller. So the amount of pixels or the number of pixels for the particles is considerably smaller.
So this is the case with no object. So we just plotted out the pixel intensities, like what distribution of pixel is lower and what is higher, so that we can select some thresholding criteria or normalizing criteria. So it's just to show that when there is no object involved, you just have a black background in the particles, then this is something what you see.
Okay. Yeah, that makes sense. Thanks.
Hey, can you guys say, maybe to put this in context for the rest of the class, maybe can you describe what you guys did with regards to the magnification and how that was different from lab 2?
I think
You can go to that image.
which slide?
The experiment, yeah. That.
I can give you the control.
Oh, it's later. Sorry.
So at least in our case, the magnification was not changed from lab 2. Like we used the plane sphere for lab 2 and Spiky 1 for our project. But yeah, Pranav, you have to add something.
So what we did was actually we moved the camera further back. So the object that we were looking at after we bought the balls were actually much larger. So if I go here, this ball that we had, or this plane sphere that we had, was actually much larger than the different models that we had already present. So for example, the biggest model that was there already in the lab was 38 mm long. However, our sphere was basically 43 mm, so it was larger. So what we had to do was we had to move the camera back to actually increase the magnification, and that is why we were able to capture a bigger field of view. as well as we had to use a 15 mm lens so that the laser light, the laser sheet that we generated was actually large enough, or was at least 4 diameters or 5 diameters larger than the model that we had, so that everything in the field of view was illuminated. So you can see the field of view here, the particles here, and the model is there. And so basically that's how we designed the whole system.
Yep, very good. So yeah, they moved the camera back. But what was the consequence of that on particle size?
Oh, we got particles. Yeah, go ahead.
The particle size did become smaller. So in a PIV system, we want the particles to be at least 3 to 5 pixels large. However, the consequence of that was our particles were somewhere around 1 pixels. So that could have been one of the reasons that added the uncertainty in our results. But that is the data that we had, so we had to go with it. But if we were to repeat it, we would actually add more particles or increase the intensity of the light, do something else to increase the size of the particles in the images that we were getting.
I think our data was a bit more certain because we had like 150 images. So if we have more uncertainty, it's just we have a larger data set. So our particles were sub-pixel. It was less than a pixel. It surely added more uncertainty, but just having a large number of having a larger data set helped us reduce that uncertainty as well.
Yeah, good answer.